Our short homework. Okay, so for the first question is the basics. Solve the following recurrence relations question. And for what we have learned, for the first example, we have AR minus 7 AR minus 1 plus 10 AR minus 2 equal to 3 to the power R. So as we told in class, we have to first find the particular solution and then find the homogeneous solution. Or you can use you can use generating functions to solve this recurrence relation. But for the first method, we can get a particular solution because we have equal to 3 to the power R. So by experience, we can guess the particular solution is something times 3 to the power R, and we put in something times 8 to the power, so something times 3 to the power R to solve it. We can get AR is equal to negative 9/2 times 3 to the power R. And next, we want to get a homogeneous solution. So to get a homogeneous solution, first we have to get a characteristic equation, which is x squared minus 7x plus 10 equals 0. And so solving the characteristic equation, we can get x is equal to 2 or 5. So we can get the homogeneous is something times 2 to the power R plus something times b to the power R. So we get total solution AR is equal to the sum of particular solution and homogeneous solution. And we know A0 and A1 equal to 0 and 1 is respectively. So we can get AR is equal to negative 9/2 times 3 to the power R plus 8/3 times 2 to the power R plus 11/6 times 5 to the power R. And for the next question, it's also similar. First, we get a particular solution is equal to 0, and we get a characteristic equation, and get a homogeneous solution, which is also equal to the total solution because the particular solution is 0. And then we put A0 equal to 0, A1 equal to 1 here. Sorry, typo. I should check my answer again, but A0 is 2, A1 is 1, and A2 is 1. We put it in and get the final solution. So is everyone okay with this? Okay. And for the question 2 is want to solve the following recurrence relation, but here we got AR squared minus 2AR minus 1 squared is equal to 1. So the hint we get here is we let BR equal to AR squared. So if BR equals to AR squared, we can get BR minus 2BR minus 1 is equal to 1. And B0 is equal to 4. And we solve the recurrence relation for BR first. We can get BR is equal to 5 times 2 to the power R minus 1. And finally, we can get AR is equal to square root of, another typo, 5 times 2 to the power R minus 1. And for part B, here we got AR squared minus 2AR minus 1 equal to 0. So the hint is defining a property Bn as in part A. So here we let BR is equal to log AR, Where here LG log, it means log with 2 as the base. So we can get AR squared. First I move 2AR minus 1 to the right hand side. We get AR squared is equal to 2AR minus 1. And we replace AR squared with 2BR. And 2AR minus 1 is equal to 1 plus BR minus 1. And B0 should equal to 2. So we can get, so for the recurrence relation, we can get BR is equal to 1 over 2 to the power R plus 1. So the final answer, AR should be equal to 2 to the power 1 over 2 to the power R plus 1. So is everyone okay with this question? Yes, okay. And for question 3, for each of the following recurrence relation, find the generating function where R is the coefficient of x to the power R. So this is also the type of thing we practice in class. So for part A, we summing up from R equal to 2 to infinity and times the whole equation with x to the power R. So we can get AR, the summation of AR x R is start from R equal to 2 equals to x minus A1x minus A0. And for the second part, we have 5. First, we take x out. We got x AR minus 1 times x to the power R minus 1. So we get AX minus A0. And for the next part, we got x squared times 6 times AR minus 2 times x to the power R minus 2. So we get 6x squared times AX, where AX is the generating function we want to find. And simplify it, we can get AX is equal to 1 minus 5 plus 6x squared. 0 divided by 1 minus 5 plus 6x squared. And for part B is similar. So for the right hand side, we have summation for I start from 2 to infinity. Then we have 4 to the power R plus 6 times x to the power R. And the right hand side will equal to 16 times x to the power 2 divided by 1 minus 4x plus 6x squared divided by 1 minus x. And for the left hand side is the similar procedure as the previous question, and we simplify it to get the final generating function here. Is everyone okay with it? Yes, okay. And for question 4, this is a little harder. Let AR denote the number of non-overlapping regions into which the interior of a convex R-gon R-sided polygon is divided by its diagonals. Suppose no 3 diagonals meet at one point. So for the first part, we want to show that AR minus 1 is equal to R minus 1 choose 3 plus R minus 2. So, okay, so first, let me see what does R minus 2 means. So assume that here we have a R minus 1 sided polygon here. And we adding one new vertex to the polygon and drawing all the diagonals starting from this diagonal, from this vertex. Sorry. So in this part we have R minus we have 1, 2, 3, 4. Sorry, we have r minus 1. So yes, we have r minus 3 diagonals here. So the region, the number of new regions in this new area is r minus 2. And for the r minus 1, choose 3 part. So this part is the number of new region formed in the old area. So how to form or how to divide the old area to into 2 areas. So when one of the diagonals starting from A goes through an old region, the old region will be divided into 2 regions, and so we have 1 more regions in the old area. And when it goes through the old region, it actually also goes through one of the old diagonals. It also goes through one of the old diagonals, or the line EF, to go through an old region. So instead, we can count the number of such crossings where a new diagonal crosses with an old diagonal, or EF. So how to count it? Counting it. First, we have to select one of the old vertices for A, B to ending it, and then we choose the old diagonals. So to continue it, we can just have selected any combination of B, C, D, and make the middle one as the end of the new diagonals, and the first one and last one as the old diagonals. So we have to choose 3 vertices from the r-1 polygon, the old area. So the number of lane is r-1, choose 3. So this part is very difficult. Is everyone okay with this part? Okay? Okay. So for part B, we want to determine a generating function where the coefficient of x to the power r is AR. So we are using the old method here. And notice that by definition, the recurrence relations starts from r is greater than or equal to 3. So to sum it, we have to start from r equal to 3. And we have AR minus NR minus 1 times x to the power r is equal to this crossing times x to the power r. And to get the generating cross form of this part, we can try to differentiate 1 over 1 minus x, which is equal to 1 plus x squared all the way up. And we can get x minus x times x is equal to x to the power of 4 divided by 1 minus x to the power 4 plus x to the power 3 divided by 1 minus x to the power 2. And finally, we can get a to the power x is equal to this generating function, where here we have 1 minus x to the power 5 and 1 minus x to the power 3. And after we get a generating function, we can get the closed form of AR. So for these two generating functions, we want to get the coefficient of s. We can imagine the bottom part as a generating function for distribute identical balls into buses version. So for this part, we first move x to the power 4 out. We want to get the generating function of 1 over 1 minus x to the power 5. So we have the generating function is r minus 4 plus 4, choose 4. 5 boxes and r minus 4 balls. And for this part is similar. So we can get AR is equal to r, choose 4, plus r minus 1, choose 2. So is everyone okay with this part? Okay. So for question 5, let Bn denote the number of n-bit binary string in which the pattern 01001 occurs at the nth bit. Find a generating function for B0, B1, B2. And for part B, let Cn denote the number of n-bit binary string in which the pattern 01004 first occurs at the nth bit. So here we follow the definition of occurs as we define in class. But if you are just solving the number of strings ending with 01001, I think it's also okay, because the occurs is not well defined in this homework alone. So whether you are following the definition we discussed in class is both okay, but now I'll follow the definition defined in class. For every string ending with 01001, the pattern can occur at the last bit. But it's also possible that we have something like 01001 and then 001. Then the 01001 occurs as a n-3 bit. So we can get the recurrence relation is equal to Bn minus 3 is equal to 2 to the power n minus 5. The number of string ending with n minus 5. And we use the OR method here to find the generating function. But here, for convenience to satisfy, but also to satisfy the recurrence, I define B0 is equal to 1 and B1 to B4 to be 0 for this part and the next part. Then we have Bs is equal to x to the power 5 divided by 1 minus 2x times 1 plus x to the power 3 power plus 1. And for part B, we want to find the number of n-bit string where 01001 first occurs at the nth bit. So here we consider the number of string where 01001 occurs at the nth bit, but not first. So there are several cases. First case is First case is it occurred. The nth bit is also the first time it occurs, or it occurs at the n minus 5 bit, and then we end with 01001, or it first occurs with the n minus 3 6 bit, and then the remaining 6 bits it occurs again, so on. So So we get this recurrence relation. And for convenience, also to satisfy the recurrence relation, we set C0, C1, C2 to C4 is equal to 0. So that we can rewrite it as Cn times B0 plus Cn minus 1 times B1 all the way up to C0 times Bn. So then we times both sides by x to the power n and sum them up. And let this thing be Bs. And we have B0 is equal to 1, so we minus 1 here. And this part is equal to Bx times Cs, the summation of the two generating functions. So we know what Bx is, and so we can solve Cx to get this generating function. So is everyone okay with this? This is just the same as a thing we just discussed in class. And for question 6, a coin is tossed 2n times. How many of the 2 to the power 2n outcomes have the number of heads and the tails equalized for the first time after 2n tosses? So we gave the key, compare the values for the cases where n equals to 1, 2, 3 with the Cartan numbers. So first consider, assuming the first toss we get a head. And because at a 2n toss, the number of heads and tails equal for the first time. So the next toss must be a tail. And if we replace the heads with parentheses and the tail with the right parentheses, then we can write the sequence of the head tails as a form of the way to write parentheses. So as you can see in the progress, during the progress, the number of the tails, if we remove the first toss and the next toss, during this progress, the number of the tails can not be greater than the number of heads, or else in the whole process, there are some point in the middle where the number of heads and the tails are equal. So the middle part is actually the way to write the number of ways to write a parenthesis, which is the Cartan number corresponds to the Cartan number we discussed in class. So for this case, if the first toss is a head, the possible number of length is Cn minus 1, where Cn minus 1 is the n minus 1's Cartan number. And for the case where the first toss is a tail is very similar. We replace tail with the left parenthesis and head with the right parenthesis. We can get the same numbers. So the number of such sequences is 2 times Cn minus 1. Yeah. So is everyone okay with this question? Okay.